Thanks already for the kind and great introduction, and thanks for giving me the chance to present a couple of our work of our scientists and also of our partners in the industry. So I picked the title, Therapeutic Oligonucleotides and Chromatography, What's New? I think I had quite a similar title like that 3 years ago when I was first presenting at TIDES. So I thought just reuse it because in the 3 years there's a few new things happening and coming, what I want to talk about today. How I structured the presentation is to just take a look at what are the different impurity classes that we're seeing at oligonucleotides and how to purify them or analyze them using chromatography technologies. So throughout my presentation, I will take a look at those impurity classes that are seen here. I know there's many more, but for the interest of time, I focus on these that are here on the slide. So the first one, which I think is the most common impurity, it's just looking at the short-mer and long-mer purification and analysis. Just for those who are not familiar with chromatography and how it works, I think a lot of you are familiar with how nucleotides look like. We're basically using the phosphate backbone, so the longer a nucleotide is, the more negative charges it carries, and then we can separate according to these negative charges. How does it look like in chromatography? So we're separating according to the charges, so we're using ion exchange chromatography, typically anion exchange chromatography, and that's how such a chromatogram looks like. So we load at low salt concentration, and then we have an increasing salt concentration, typically a linear salt gradient, where we first have the short-mers eluting in the center. We have our full-length product, what we want to get, and then in the later part, we have the long-mers eluting. Typically, if we're developing a process, of course, we want to have the best resolution between our impurities, short-mers and long-mers, to our full-length product. There are technologies how you can improve that with smart continuous recycling, but I think one very important factor is the resin and just the way you design the process in terms of salt, buffers that you're using, how much you load. But what you want to have is basically have as little overlap between your short-mer impurities to your product or your full-length product and your long-mer impurities to your product pool. So here's just one short example of comparing the TSK Gel Super Q5PW20, which is a product of Tozo, against a PSDBB-based competitor resin, first at a quite low load of just 1 milligram per milliliter. And here we see this quite nice separation on both of the resins for the N-1, the N, and the N+1 peak. But typically, if we're thinking about large-scale processes, you of course want to load higher capacities. So we looked at the same thing at 20 milligram per milliliter. And what we set here as just comparison metrics is to say that we want to have over 80% recovery in our final product pool. And with keeping this point constant, we were able to achieve 96% full-length product purity on the Tozo material, compared to on this competitor resin, we were only able to achieve 90% purity. So I think a lot of you are familiar already with the Super Q5PW, especially if you're working in the oligo purification field. But I said there's new things coming, so we will be introducing soon the successor of this resin, and we will call this Super Q4PW. So just looking at the specs, so the bead size, it's the same, it's 20 micron, it's also a polymethacrylate backbone, but the big difference is that we tailored the pore size, as oligonucleotides are typically rather small molecules, so we don't need the 100 nanometer pore size, so we decreased the pore size going down to 50 nanometer, and we already see that this has a big impact on the binding capacity. So with short 20-mer oligonucleotides, we could almost double the binding capacity, and with a longer 100-mer oligonucleotide, we have something like 60-70% more binding capacity. This is just a high-level overview, but we tested it with many different oligos, and on average, I would say we were able to achieve 80% higher capacity. But I think, having more capacity, it's nice and good, but in the end, you want to see how it behaves when you're actually separating something. So we provided a prototype of this resin to many partners in the industry. And I want to thank LGC Axolabs, so especially Martin Kögler in Kulmbach. He did a very nice study, and he and the management allowed me to present a couple of those slides here, so thanks to them. So in this case study here, it was a 41-mer RNA with 2O-methyl endings on both of the sides. Unfortunately, we couldn't show the exact details of the sequence, so that was something that was just briefly edited out beforehand, but it's a 41-mer RNA. This is just the crude analysis after synthesis. So with using anion exchange HPLC, it was around 54% purity, with IPRP 44% purity. So let's say an average, roughly 50% crude purity after synthesis. Then in their study, they looked first at the dynamic binding capacity. So here it's just showing the breakthrough curve of the new resin, the Super Q4PW. And then so basically here they loaded the resin until 10% breakthrough and then just did the elution of everything that was bounding to the column. And here they identified roughly 10% higher dynamic binding capacity on the Super Q4PW. And then they were able to load roughly 44 milligram of crude feed onto the resin, which translates to roughly 20 milligrams of full-length product onto the oligonucleotide. Or if you're speaking in ODs, it's roughly, 1,300, 1,400 OD per milliliter. Then, as I said, they also eluted here everything that was binding to the column later on. And a nice effect is that we're having here a slight breakthrough of material, and then of course we stopped at roughly 10% breakthrough. But the interesting part is that everything that was breaking through was short mers, which also makes sense from the theory, but just by already overloading the column to a certain extent, they were already able to roughly increase the purity by 12-13%. And this is actually with the anion exchange HPLC. So this was where we had, I think, 54%. So let's say 7-8% purity increase just by overloading the column. So I think that is also already a nice takeaway, that especially if you have a lot of short mers, because you have these displacement effects from longer oligonucleotides, it might be actually beneficial to just overload the column and be okay with everything that's breaking through, because typically these are anyways your impurities. Then, of course, the interesting part is when it comes to a gradient elution. So here is a comparison of 5PW, so our existing material, to the new resin, the 4PW. So starting with the 5PW. So here in this case, the column, so it's a 5 milliliter column, was loaded with 163 milligrams, so almost, let's say, 28 something mix per milliliter. So basically 80% of the dynamic binding capacity, and then just ran a standard linear gradient. There was no real method optimization, so it's more or less the standard protocol. And then, of course, this was fractionated and then looked at the individual fractions. So here's just showing you a few of those fractions that Axolabs looked at. The important part is just now figuring out which of those fractions do we need to pool. And the idea or the goal that we discussed is that we will just pool everything that has a purity in the individual fraction above 85%. So here are just a few of the analytical chromatograms. So the early eluting stuff, let's say 1D1 until 1F2. So if we just go back one slide, so that's everything here on the left. That was mainly our short mers. So just a little bit of full-length product, everything that we had in the center, so from 1G2 to 1E4. So going back, it's from this point to this point. This is actually the pool that Axolabs pooled afterwards, and then everything in the back from 1G4 onwards didn't have this 85% purity anymore. Looking then at the overall results for the pool, so here's just the fractions that were pooled in the end. So overall, the recovery, they had roughly, they had 14 milligram per milliliter of full-length product that was in the end recovered from the column. the purity of the pool was around 90%, and the recovery of everything that was put on was roughly 79%. So now the interesting part is how does this result compare with the new developments of TOSO. So it's exactly the same setup. We loaded again, or Axolabs loaded to the SuperQ 4PW, in this case, again to 80% of the dynamic binding capacity. So this is roughly 10% higher loading because we had 10% higher dynamic binding capacity than the exact same method, exact same setup. Again, looked at the different fractions. Again, pooled all the fractions that had 85% purity. If we just take a look at this here, we can see that in this case there were a lot of these early fractions that didn't really include a lot of the product, same as with those late eluting fractions. They also did not really include a lot of product, which then also shows in the results. So we were able to recover roughly 20% more material. So the purity, last time it was 89%, now it's 91%, but I think the really nice part is we went from a full-length product recovery of 78, 79% to almost 100% full-length product recovery, which in the end means no matter what your spec are, probably would get better results with the new resin. So these were really results that I'm quite thankful for that Axolabs allowed us to present it right here. And also, if you are interested to get your hands on the resin right now, please feel free to talk to me, come by our booth, and we can gladly provide you a sample to also test it for yourself. Then looking a little bit more about what can you also do with ion exchange chromatography, not so much on the purification side anymore, but from the analytical side. And I think it's a well-established technology to use anion exchange as an analytical tool. We also saw it here in the data of Axolabs. But something we have investigated also is the use of anion exchange combined with multi-angle light scattering. So what does multi-angle light scattering give you? It's basically gives you the molecular weight and the size of molecule. It's not as detailed as with a mass spec, so you won't be able to differentiate between certain modifications, but it's good enough to differentiate between n-1 and n+1 if you get everything right. And that's just a first proof of concept application that we have run in our laboratory to show that you can also use multi-angle light scattering not just with an isocratic size exclusion method, but it actually also works with the gradient. So here the idea is just, we took a standard 20 mer, so the calculated molecular weight is 6,122 Dalton, and in the end, using multi-angle light scattering, we determined a molecular weight of 6,040 Dalton. So it's not perfect, but it's good enough to say, okay, this is our 20 mer product. And the idea is not really that this replaces mass spec in any way, but I think that could be a nice application moving forward to help like the peak fractionation in a PAT setup. So you would not attach this to your HPLC during the analysis, but you can attach this to your purification skid to real-time measure the molecular weight and then perform peak cutting based on the average molecular weight, which just gives you a better way to optimize your purification process and look at or increase recovery or increase the purity. Okay, this is the part to the short mers and long mers. Again, if you're interested, stop by and we're happy to provide you with some samples. Then let's look at the next impurity class, which is the incomplete distillation and impurity or impurities stemming from this. Bear with me, I'm not a chemist, so I'm a bioengineer by training, so I don't understand everything in detail about the chemistry of oligonucleotides, but what I understand is if I see these circles, it means it's hydrophobic. So the part is, just for the sake of my presentation, everything that I call DMT on is our oligonucleotide with the DMT protection group, and everything that I will be calling DMT off is the oligo with the cleaved, where the DMT group is cleaved off. And as I said, the protected or DMT on oligos, because they cover or carry this DMT group, are far more hydrophobic than the unprotected oligonucleotides, and we can use this difference in the hydrophobicity to purify one from the other. Another point about DMT is that typically this DMT group is cleaved with an acidic step. So you have your DMT on oligo, put it into a reactor for a couple of minutes or hours. And because this connection is acid labile, you can cleave off the DMT group from your oligonucleotide. And something that I have presented already 3 years ago, that we can, using HIC, we can effectively bind a DMT on oligo to the column, and then by decreasing the salt concentration, we can elute that DMT on oligo from the column. But the idea that we had in between, or since those 3 years, is now, can we also immobilize basically this DMT on, or bind the DMT on oligo on the column, and then just stay at high salt concentration and decrease the pH to have the DMT on groups, or the DMT group at that point, still sticking to the resin, whereas our oligonucleotide that now does not have the DMT group anymore elutes from the column. So how does that look like in a process? So we bind at high pH and a high salt concentration. Our DMT off, typically our short mers, they are directly in the flow through, they don't bind to the columns. And then we have our protected, so I think we can all agree this is a well-protected oligo. This is like our full-length DMT on oligo, this binds to the column. And then in the next step, we keep the salt concentration high, but we decrease the pH value. So this means the protection group gets removed or gets cleaved off because it's acid labile. The full-length oligo, now without the protection group, will not interact anymore because it's far less hydrophobic. So this elutes. And then in the last stage, we decrease the salt concentration and we can elute our DMT protection group from the column. So it's also here. 3 years ago, I presented something on the tauryl phenyl 650M. But also here our R&D team in this case did a great job in also designing or coming up with a new resin, especially for this application. So this will be called TSK-gel phenyl 3PW20, also coming out next year. And here we have also average bead size 20 micrometers, average pore size in this case even smaller than with the Super Q4PW, 25 nanometer. But again, the idea behind decreasing the pore size is just, you can imagine if there's more small holes in a particle, it just creates more accessible surface area. And we can see this in the binding capacity. So looking at 1 molar ammonium sulfate, we were able to roughly increase the binding capacity by a factor of 2.5. If we go to 1.5 molar ammonium sulfate, we were actually able to almost increase it by a factor of 4 to 4.5. Now let's have a look at this resin in action. So as a first proof of concept, we just tried to test our theory. So we bound at high salt, just a quite low load, just 0.2 milligram per milliliter of loading. So here our full-length product is flowing through. Then at this point, we just make make this pH shift. We still keep the salt concentration high, but shift the pH to roughly 3. And then we identified in this first step how long do we need to hold it to get a sufficient DMT cleaving. So investigated hold times of 0 minutes to 120 minutes, and then analyzed just how much DMT on to DMT off conversion did we get. And this is something we analyzed here using reverse phase chromatography. So without having any hold time, so just by decreasing the pH and flowing immediately through, we have almost no conversion of DMT on to DMT off, so just 7% conversion. But when we hold, so basically we flush the column with 1 to 2 column volumes, then we wait for 120 minutes with the low pH solution standing in the column, and then we have almost 100% conversion, so in this case 93% conversion from DMT on to DMT off oligo. But again, this was with a low load, so 0.2 milligram per milliliter. So then we scaled this up to like loadings that we would assume that we get in a large-scale process. So here it's 20 milligram per milliliter, so this is 80% of our dynamic binding capacity, so 100-fold increase from the previous experiment. Everything else is identical in terms of the run conditions, and at this point we held the low pH for 120 minutes. Now, looking at this point into the results, we can see in our load feed we had a lot of DMT on oligo with all those DMT off short mers. In our flow through and wash fraction, we have all of those short mers eluting. In our elution fraction, we have just our DMT off oligos, full length product with a little bit of N+1. And then in the cleaning step, we then remove, or we see that there is no oligo left, and the DMT group itself just didn't show here in the analysis. So that worked out also quite well, and also the same case here. It's a resin that's coming out next year, so it's not officially commercially available, but if you also want or already want to test it in a small scale setting, feel free to reach out and we can also gladly provide a sample. Then looking at the last point, or the last 3 points about other protection group modification or conjugations. There has also been a presentation roughly an hour ago looking at this. It's about hydrophilic interaction chromatography, so HILIC for oligo analysis. So I think a lot of people use anion exchange or reverse phase chromatography, but I think HILIC is more a niche application so far for oligonucleotides, and it separates by hydrophilicity. So it's basically just the opposite of how reverse phase chromatography works. So in reverse phase, we bind with water, we elute with organic, and everything that's more hydrophobic elutes later. With hydrophilic chromatography, maybe just open this slide here. So we have everything that's more hydrophobic elutes first, and then with decreasing hydrophobicity, we get the elution. I'm just going back again to this slide. An important part why this is interesting is because, of course, it just also uses solvent and water, so it's very well compatible with mass spec. And you don't really need these IP reagents, because typically what's being done is IPRP, which to me, from my background, is more in the protein world, is always a little bit surprising, because my understanding is IPRP, you have this ion pairing reagent that actually interacts with the electrostatic groups. It has a hydrophobic tail that you're basically using then in the reverse phase to separate it, but what you're actually doing with IPRP is a separation by charge and not really by hydrophobicity. Because this ion pair reverse or this ion pairing reagent interacts with the charge of your oligo. So you're separating by charge even though it's a hydrophobic interaction chromatography. So I'm always wondering why people use ion exchange and IPRP, because in my opinion it's not really orthogonal. Whereas I think with using HILIC, this is really an orthogonal method, because you're really separating according to the hydrophobicity, even if it's here maybe the hydrophilicity, but it's the difference in hydrophobicity. And then just looking at a few examples here, and which is also what I think is quite nice by using HILIC, because you can really identify these fine differences in the hydrophobicity. So here we have a 20-mer full-length product, and then a 20-mer same sequence, but just a phosphate group, or like fully tioated, and then just the phosphate at position 1, phosphate at position 10, phosphate at position 1 and 10, and then a 19-mer with the 3' nucleotide missing. And if we analyze them with HILIC, we see that we get, so these are not, this is more an artificial look at, so we just individually injected all of these molecules, but we see that we get a very nice separation of these just slight differences in the oligonucleotide sequence, which is typically something that's not seen with IPRP. And then just also looking here in this case, as I said, this is something that can be also run with mass spec, because we just have basically mass spec compatible buffers and acetronitrile. So here this is just, in this case, miravirsan. So a 15-mer full-length product, again with different impurities, but we can also see here that we get a good separation with just minor impurities being separated by almost 2 minutes in residence time. And then, of course, you can also have a look here with the mass spec, do the deconvolution, and really get the detailed information about the oligonucleotides that you're separating. So that might also be a nice idea to complement what you're already doing in your analytical portfolio. So instead of just doing anion exchange and an IPRP mass spec, maybe an idea to also investigate a little bit also hydrophilic interaction chromatography. That brings me to the end of my presentation today. Just to summarize, so we briefly talked about anion exchange purification and the new developments that we have ongoing there. I gave a short glimpse into how a potential PAT, process analytical technology application using multi-angle light scattering could look like. And I think that is something, especially 3, 4, 5 years in the future, that could be really a nice boost again in productivity, purity, and recovery of oligonucleotide and peptide applications. We had a short look into the purification of DMT-on oligos using hydrophobic interaction chromatography, and we looked at the Hillig MS analysis. So with that, I would like to thank you for coming to the presentation, for listening, for your attention. Again, I would like to thank Axolabs for providing the data. And now I'm open for any questions, and if you're too shy to ask your question here, you can also come by our booth at number 708 and come talk to us. Thanks for your attention.